Okay, here we're going to keep going. We're going to apply Bernoulli to solve fluid flow problems in combo with continuity and the other things that are in our tools bin. Okay, so here's what we're given. We're given this pipe. The pipe, the fluid flow kind of goes through this pipe. Maybe I'll do that in like a blue color or something. So the fluid flow goes through this pipe, goes this way, and then it goes out that way. One thing we'll note is this fluid is not water because it has a specific gravity of 0.86. And it's got this interesting manometer. So the manometer, kind of goes here and then it comes up and it goes that way. Okay, now notice inside the manometer, it's hydrostatic. So we can use a manometer equation inside the manometer. So this is a very, I would consider this to be about as hard as Bernoulli problems can get. And we're looking for the flow rate here. Okay, so we've got a lot of tools to work with, but some of them are a little bit complicated. And most notably, the most important thing to note with all of this is that this manometer at this end that I'm erasing right now, notice that the end is kinked into the flow. Okay, so this end that I'm erasing now, okay, notice that it opens perpendicular to the flow, but right here, okay, it opens into the flow. Now what does that mean? That means we got a stagnation. Okay, so that means that there's a streamline that comes right here and it kind of stops right there because it is static inside the tube. Okay, so what that's going to do is that's going to drive up the pressure. We're going to have a higher pressure at that point because of the stagnation point. If you don't remember how that works, go back to the last lecture, but basically we've got a certain amount, as the fluid approaches, basically a certain amount of the velocity in the fluid is going to be converted to pressure by the time it halts right there at the stagnation point. Okay, so maybe we'll the stagnation point will be kind of I was hoping to draw a star, but it looks like I drew a snowflake. Okay, anyway. So let's go ahead and try to solve this. We're looking for Q. Okay, so if we get Q, basically the way we get Q is we solve for the velocity. We can either get the velocity up here, we can get the velocity down here. We need the velocity somewhere where we have the area. If we get the velocity somewhere where we have the area, then we can get Q, because Q equals V times A. Okay, so we're going to do Bernoulli. And Bernoulli is a little bit tricky, right? Because, well, we have to know if we can. So let's think about this. So again, I'm always going to do this while we're learning Bernoulli, and then, we're learning how to deal with these assumptions. And so the first assumption is always, is this flow steady? Okay, and we're just going to have to go with yup, because we don't have anything saying that the flow rate is changing. Okay, what about 2? Okay, so is this inviscid? Okay, so basically we're saying, is there friction in this thing? And then, of course, the answer is always no, because there's certainly friction in this pipe, but we're going to assume yes. Okay, and that may bother some of you guys. It's no different than when you're in other classes and they say, oh, we have a frictionless pulley, or, we've shot this ball through the air, ignore wind resistance. It's the same thing. We're assuming no friction. That we will learn how to deal with that, and we will actually give a realistic, we'll deal with that realistically, which this is the first class where we ever really do that. Before that, it's always frictionless springs and things like that. So this class, we will actually deal with it. So it's something that I think is kind of cool about this class. Anyway, so incompressible. Okay, is this fluid incompressible? Well, based on its specific gravity, 0.86, it's basically the same specific gravity as water. I mean, it's 0.86 of water. So we can assume that this is a liquid, and so we're going to go ahead and say yes, that this is incompressible. And then the last thing we want to know is, are our 2 points along a streamline? Okay, and the thing is, we don't know yet because we haven't picked our points. So we're going to have to pick points along a streamline. So let's pick our points. And so what we want to do, and when we pick points, okay, so where do we pick points? Okay, well, there's one thing I told you in the last thing is if you can, you basically want to go where you have information. Okay, where do you have information? Okay, and a lot of times the best place is, based on last time, as I said, if you can get somewhere where you're in the open to the atmosphere, that's a great spot. Because if you're open to the atmosphere, then you have no pressure, and that makes things super easy. However, in this case, none of this is open to the atmosphere. You see the way I've drawn these pipes with these kind of little, I don't know what you call it, but basically these pipes continue on indefinitely. Like we don't know where they stop. So if that's the case, then these things are not open to the atmosphere, so we can't do that. But where do we, well, the manometer is a huge thing. It tells us information about the pressure. Okay, so we want to use that. Okay, so we want to see if we can't use the ends of the manometer. So right here is a great point. We call that point 2 because I like to have things flow from 1 to 2. And I would like to make point 1 right here, but there really isn't a streamline that goes from 1 to 2. So instead what I'm going to do is I'm going to assume that that thing has some information about the pressure right next to it, which in fact it does. Okay, and it's just that this is a funky manometer. Okay, right, if the manometer were perpendicular to the flow as it is here, then I could use this point right here, but I cannot do that. So instead I'm going to use this point right here. I'm going to call that point 1. Okay? The other thing I like about both of those locations is I have the areas. Okay, so I have information about those. I have the cross-sectional areas. Okay, so let's go ahead and let's do what we have been. We're going to try to use Bernoulli as our master equation and see if that will solve it for us. All right, so there's Bernoulli, the great and powerful. Okay, and so this really is a challenging problem. So I don't want to belittle this problem at all. Like this is, we're having to fight for this championship here. It's not, no one's going to give it to us. Okay, we're going to have to work. All right, so one thing I want to note is that these gammas, this is gamma F of whatever this fluid is. Okay, so it's going to be 0.86 times water is what those gammas are going to be. So let's start with pressure at 1. Do I know the pressure at 1? Okay, no, I don't know the pressure at 1, right? In fact, it's really hard to figure out anything about the pressure at 1, so I can't really do anything with that. What about the pressure at 2? Do I know the pressure up here? No, it's inside of a pipe. Okay, I don't know anything about it. Now, usually if it's inside of a pipe, we're going to need to get at those using the manometer, and luckily we have a manometer, so we can do that. Okay, what about Z1 and Z2? Well, luckily we can kind of get at Z1 and Z2, and let's see, because we'll do this. Okay, here's Z1, so that's going to be the datum. Okay, and I'm doing that because I don't want to deal with it, so we're going to make this 0 because it's the datum. To get to Z2, we're going to have to deal with the fact that I drew this a little bit incorrectly. Okay, so let me change this a little bit. I'm going to have this, well, I want to do this in black. I'm going to have this line go down basically to there. Okay, so this is right over here. Okay, so Z2 is going to be 5 feet. Okay, so 5 feet. Now, usually, because it's 5 feet from here up there. Okay, now usually these little, these stagnation tubes right here, this opening from here to here is a negligible distance. Okay, so basically, you can basically say that's 0 most of the time. So that's kind of why I drew it incorrectly, but that's really how you do it. Okay, now V1 and V2, well, we don't know anything about V1 or V2, right? Because it's just flow in a pipe. Okay, so to get V1 and V2, we're going to need to use continuity here. Okay? So basically this equation, this Bernoulli equation, is going to end up being our master, but right now we don't really know a whole heck of a lot. Okay, so let's just leave it like this. I could spend some time rewriting it, but let's leave it like that and we'll come back to it in a second. Okay, so we're going to use it as our master. Let's deal with these pressures. Okay, so we got P. So I'm trying to get P1 and P2. Okay, I can't really get P1, but I can kind of get at like a P3, I guess. So like if I redraw this. Okay, let's take this point right here. I'm going to call that point 3. Okay, and so I can kind of like maybe sort of figure this out. So I'm going to do a manometer over here. Give myself a little bit of space so I can write the word manometer here. So we're going to do manometer equation. Okay, and so we're going to start with pressure at 3. Pressure at 3. Okay, now I'm going to be working upwards. I'm going to go over. I'm going to work back down. So the net effect of that is just to go to the right. So that doesn't count for anything. And then I'm going to go down some bit. I don't know how much that bit is. Okay, so I'm going to go down some bit. So what do we want to call that? Well, I need a name for it. Why don't we call it h? Okay, so if I go down h, that's going to be plus, because I'm going down, gamma of the fluid times h. Okay, so now I'm going to keep working, and I'm going to go horizontal through that fluid, and I'm going to go up 0.8 times the gamma of whatever that fluid is. So we're going upwards, so that's negative gamma, I don't know what we call that fluid, gamma black, gamma B, times 0.8 feet, 0.8 feet. Okay, now we're going to keep going up, and we're going to go up this distance right here. And that distance is a little bit harder. So let's do minus gamma, that's our fluid, times whatever that distance is. And that distance is a little bit harder to figure out. And here I'm using some geometry here, but I'm going to note that on the left-hand side of this, I've got 5 feet and h. So I've got 5 feet plus h equals, on the right-hand side, whatever this distance is, plus 0.8. So let's call that x plus 0.8 feet plus this, 0.8 feet. Okay, so I'm just doing the two sides of essentially of a rectangle. So x then, which I want to plug in right here, is, let's see here, 5 feet plus h. Well, it's not h feet, it's just h. Right, it's got a feet in there somewhere. Minus 0.8, minus 0.8 feet. Okay, so we're going to put that in here. So I've got 5 feet plus h minus 0.8 feet. So that's 4.8 plus h. And so that's going to get us up here, and then we're going to cruise on over until we get to P2, so that means equals P2. Okay? So what we want to do now is I want to solve this manometer equation. So let's say P3 plus, well, let's see, gamma F is, let's just leave it as gamma F for now, H. Well, yeah, let's leave it as gamma F. Yeah, so, okay, yeah, that's good. Sorry, okay, let's remember that fluids is hard. It does not conform the way we would like it. Let's notice that the gamma FH is right here, and we've got a negative gamma FH right here if we take into account that negative sign right there. So those two are going to go away. So I'm going to be left with, well, if it will allow me to erase, it hates erasing. Okay, so let's see, we've got a minus. Come on, punk. Okay, let's see, so we got minus, come on, minus gamma, black fluid, whatever that is, times 0.8 feet, minus gamma F, times 5 minus 0.8 is 4.2 feet, equals P2. And because I know I'm probably going to plug this into the other equation, I'm going to write this as P2 minus P3. Okay, I'm going to divide everything by gamma F equals, let's see here, negative gamma B over gamma F times 0.8 feet minus 4.2 feet. Okay. Now we're gonna note real quick that gamma B is 2.5 times gamma of water, and gamma F is 0.86 times the gamma of water times 0.8 feet minus 4.2 feet equals P2 minus P3 over gamma F. Okay, and so if we solve this equation, I'll say P2 minus P3 over gamma F equals, let's see here, 6.525, okay, feet. Okay, so there you go. Okay, now that's probably really, really helpful. Okay, so we can go back up here, and our next goal is to plug that in, but oh no, we've got pressure 1, we've got pressure 2. I can't plug this in, right? I need some way to relate pressure 1 and pressure 3, and this is what makes this problem so fantastically difficult. We have to think about, so if we look here, So here's our fluid, and it's flowing past, and it's just cruising on along, and it passes point 1, and it's on its way to point 2. There's a parallel streamline that's going to point 3, okay, and it's going to stagnate. So what we need to do, and this is an unusual thing, we very rarely use this, but I want to use the fact that this is a stagnation. And what that tells me is something about the relationship between 1 and 3, because basically these two are identical. They're right next to each other. They're identical until they get right in here. Okay, and so what happens is these two have identical velocities out here and identical pressures. But then as this one approaches, the velocity along this streamline is converted into pressure right here. So basically, the pressure at 3 over the gamma of the fluid, okay, is the same as the pressure at 1 over the gamma of the fluid, except it's been elevated. It's been elevated by basically all that velocity was slowly turned into pressure. So it's been elevated by V3 or V1, because they're the same velocities. We're going to use V1. They're the same velocity. V1 squared on 2G. Okay, so all the velocity basically is converted into increasing the pressure at P3. Okay, so this is a stagnation. Okay, now that's a very complicated concept. Please ask me if that doesn't make any sense. Okay, I'm trying to teach it as best I can. I think that should make sense, but if it doesn't, come to office hours. Let's talk about it. Let's make sure we can get this. Okay, so what's nice about that is I can take that and put it in, well, I don't really want to draw that line underneath all of my future work on Bernoulli. So let's just grab this whole thing, if it will let me do that. I hope it will. Oh, well, all right, whatever. P3 over gamma equals P1 over gamma plus V1 squared on 2G. Okay, so we're just going to take that over here. Oh, son of a... really struggling over here. Okay, so the other way to put that is that, okay, so we've got P3 over gamma. Okay, so here's what I'm going to do. I'm going to go down here. I'm going to say, okay, P2 over gamma F minus P3 over gamma F equals 6.5256 feet. I'm going to expand this thing out. So I'm going to write P2 over gamma F minus, okay, so this is going to be P1 over gamma F plus V1 squared on 2G equals 6.5256 feet. Okay? So what's cool about this is now I can rewrite this as P2 minus P1 over gamma F equals V1 squared on 2G. So we distribute the negative sign, bring it over to the other side, plus 6.5256 feet. That's the result we wanted. Okay, because I can take that. Okay, so this is the manometer. This is the manometer with a with one end as a stagnation. Okay, so that's just because that tube turned into the flow. Okay, so that's what makes this a little bit more difficult. Okay, so we're going to take this thing and I'm going to plug it back in up here. P2 minus P1 over gamma F. Okay, so basically I'm going to take this term and bring it over to the other side. So let's rewrite this as 0 plus V1 squared over 2G equals P2 minus P1 over gamma F plus 5 feet plus V2 squared on 2G. Okay, so P2 minus P1, we know what that is over here. Okay, so I'm going to say V1 squared on 2G, no need to write that 0, equals equals V1 squared on 2G plus 6.5256 feet. Okay, so I just plug that in for this, plus 5 feet plus V2 squared on 2G. Okay, right? This is getting like kind of annoying and stuff, right? But look, things are working out really pretty. We've got this on both sides. So that goes away. No guarantee that's going to happen for you. We've got a small Houston. We have a problem. Huh. Aha. You all saw it from the beginning, didn't you? You didn't tell me. All right, well, we've got some fixing to do, okay? And it's not really a huge fix, but this number over here should have been a negative. Notice there should be a negative sign right here. So that means there should be a negative sign right there, which means there should be a negative sign right there. Which means that this should be a negative sign, right? Okay, so we'll make this last thing into a negative as soon as it will allow me to erase. Okay, so that should be a negative sign. Okay, negative. Okay, hopefully, right, so then when we go up here, okay, this is a negative. All right, so, hopefully that's mostly fixed. So then we can bring these two terms over to the left, and we'll end up with 1.5256 feet equals v2 squared onto g. Okay, and we should probably get out of this g world because we're going to actually start plugging into a calculator. And we've got feet, so we need 32.2 feet per second squared. And we'll go ahead and solve for v2, and it comes out to, okay, equals 9.9120. Okay, that's feet per second. Okay, and now we're in pretty good shape. We just need to remember what it is that we're looking for, and it looks like we are looking for Q. Okay, so how do we get at Q? Well, we're going to do Q equals VA. So Q equals V2, A2. Okay, so Q equals 9.9120 feet per second. And we're going to multiply that times A2. What is A2? A2 is 20 square inches. Ugh, horrible units, right? So 20 inches squared times 144 inches squared and 1 foot squared. Okay, and if we do all of that, 1.3767 CFS, because we've got inches squared cancel, and we got cubic feet on top and seconds on the bottom. So we get Q equals 1.38 CFS. Okay, and that would be the solution. Okay, very hard problem. Okay, no question about it. Okay, obviously a lot of messy work, but all the work looks messy when you zoom far enough out. But most important thing here, the major weirdness is right here. Okay, I also want to note that if you get into a problem and you're like, I can't get to this point, but I know what to do if I had this number. Okay, like maybe it's like worth 8 points to get here, and maybe this is another 2 points for this. What I recommend you do on a test, at least for me, is you just go, I can't get V2, but for whatever reason, right? Show as much work as you can. You can just say, I'm going to assume V2 equals 1 foot per second, right? And then you just solve the rest of it. Q equals 1 foot per second times that area, 20 inches squared times 144, not 144, but 1 divided by 144. And what will happen is, okay, and this is feet squared like that. And then you would solve and you would get an answer. And the answer would obviously not be the correct answer. You would get whatever of these 8 points you deserve. Obviously not all of them if you couldn't get this answer, but at least you would get these 2 points, okay? Or let's suppose it's just a time issue, okay? But you know how to do this, and you can squeeze out these extra 2 points. Go for it, okay? Just assume a number so that I know what you're doing. Assume a reasonable number. Don't assume like 72.513.7. Don't assume that number. All right. Anyway, okay, so let's do another example. Looks like I just shifted this all around. Oh, this is really obnoxious. Let's do another example. Oh, look, we've got some tools. Let's bring the tools with. Okay, so let's zoom in. We already know we're going to use these tools. Okay, so you can kind of mentally just drag these tools around for you on your test. Okay. All right, so let's zoom in. This one will be less involved than the last one. We've got a horizontal Y fitting, and into this Y fitting, we've got a fluid. We'll go ahead and make it water, and it's coming in, and it's splitting as it flows through. And what we want to drive at here is, so we know the flow rate that's coming in, and we know the pressure. Okay, this G, remember, means gauge. Okay, so the pressure at whatever 0.1 is. So I guess we're going to, we already know 0.1, right? It's got to be like right here. Okay, so we'll make that 0.1. And we'll go ahead and make 0.2 right here and 0.3 right here. Okay, now why did I choose those points? Because that's where we want to know, that's where our question is. We want to know what P2 is and what P3 is. Okay, we want to know the pressure on the far side of that fitting. Okay, so again, as usual, my thought process is always Bernoulli is going to be the master. Now, that said that Bernoulli is the master doesn't mean that we always want to start with Bernoulli. In fact, usually it's kind of the slower way to work the problem because we just kind of end up on a dead end. But it does help you figure out the sort of things that you're going to need. Okay, so I'm going to work Bernoulli, and I'm going to work it right below the problem. Maybe not that far below. Okay, I'm going to work it right here. And what I'm going to do is I'm going to work it twice. Well, I'm just going to work it once. Okay, we're going to go from here all the way to there. Okay, so from 1 to 2. And then we'll come back and we'll do the problem again from 1 to 3. Okay, noting different streamlines. All right, so here's Bernoulli, right? Now, can we use it? Okay, is the flow steady? Okay, well, let's see. We've only given one Q. It doesn't look like it's changing, so we'll go with yes. Is it inviscid? Okay, well, there's no pumps or turbines or anything like that, but there is friction. However, we're going to assume that it is, in fact, inviscid. Okay, is it, I'm trying to remember these. Incompressible. Well, it's water, so we'll go with yes. Okay, is it, or are there points along a streamline? And the answer is yes. Okay, so I've drawn the points, 1 and 2, such they're kind of on a streamline. And then 1 and 3 are kind of on a streamline right next to those two. Okay. All right, so let's go ahead and see if we can solve this. Okay, what's the pressure at 1? Well, look, it's known. We know it's 20 psi-G. Okay, note, if you see psi, you should be very worried. Okay, because psi is a horrible unit. So 20 pounds per inch squared. Okay, times 12 inches times 1 foot. Okay, we're going to go ahead and square that. Okay, because we're going to do it twice to get this into PSF. Okay, because I don't want to be messing around with pounds per square inch. I guess in this problem you almost could do that because these are inches here, but still I'm not going to do it. I'm just not going to do it. So 144 times 20 is 2880. Okay, unless my brain is not functioning at the moment, which is always possible. Okay, so we'll go ahead and plug that in for P1. This is going to be gauge. So we've got 2880 PSFG. Okay, divided by gamma. In this case, it's gamma of water. So the gamma of water is 62.4 PCF. So when you divide those, you'll get feet. Okay, Z1. Well, let's go to P2. Do I know P2? No, that's what we're looking for, right? I think that's what we're looking for. Yeah, that's what we're looking for right there. Okay, so Z1 and Z2. Well, one of the cool things, and this is going to happen, so you have to recognize this, is that this is a horizontal Y fitting. So what that means is that all of these things are on the same level. This is vertically. So if they're all on the same level vertically, I'm just going to make that level the datum. And so we can go down here, and all of those points are going to be datum and datum. Okay, gone, done. Okay, and now we've got to get at these velocities. Okay, and the nice thing about this in this case is, how do we get at the velocities? Well, okay, let's go and see how we can get at the velocities. Here's our tools. Usually to get at velocities, we're going to use continuity. Let's try that here. Okay, so V1 should be pretty straightforward. So Q1 equals V1 times A1, right? So we're going to go ahead and zoom in and solve that. So Q1 is what? What was Q1? 4 CFS. 4 CFS equals V1, which is what I need for my equation, times the area, which is pi times 6 inches, which is a half a foot, squared, divided by 4. Okay, so V1 equals, let's see, sorry, I wrote this down, 20.37 feet per second. Okay, I should also note that apparently I didn't write this down, but V2 is given. It was given in this problem, so go ahead and put that into givens as 40.74 CFS, not CFS, FPS. Okay, that's an interesting, seems a little contrived to me that would be the answer right there. I wonder why. I'm thinking that this is something I did. Okay, but anyway, so this is a given. Okay, so I know V1, and now I know V2. So I go ahead and solve this sucker by plugging in for V1. Right, yeah, so now I can solve this whole thing, because now I know this one, and I know this one from continuity. Okay, so V1 is going to be 20.37 feet per second squared over 2G. In this case, remember G is 32.2, because I'm working with the dumb system, 62.4 pounds per cubic foot, plus, and then V2 squared. What's V2 squared? Oh, it's given as 40.74. I'm going to not write the units right now, so I can squeeze it in there. And divided by 2 times 32.2 feet per second squared. Noting that these units do work out right here, even though I didn't write them. They will work out, because of feet per second it's going to be feet squared over second squared, divided by feet per second squared. So we'll end up with feet for this whole term. Okay, so if I solve this whole thing, I'm going to get P2, and it's going to be give me 1 second. 1670.4 PSFG. Okay. Now, usually what I'm going to do with problems is, if it was given to me in PSI, I'm going to respond to it in PSI. So that's going to be equal to 11.6 PSIG. For my class, of course, as long as you use a reasonable units, unless I ask for something else, I will accept whatever you give me. Okay. Don't give me like pounds per square mile or something. That would be really annoying. Okay, so now we need to get P3, noting that essentially we have almost the exact same equation. Now what I want to do here is, I want to note that everything on the one side is going to be exactly the same. So what I'm going to do, I guess, is let's do this. Let's go like this. Nope, it doesn't like that. I was hoping to be able to copy and paste, but let's see what we can do. So 2880 PSFG over 62.4 PCF. Notice it's the same point. So there's no reason to reanalyze everything. Okay, 2 times 32.2 feet per second squared equals. But now I'm going to go to 0.3. So I'm going to go 0.3 over 62.4 PCF. Okay, the Z is still the datum, but I need to get V3. So like right here, I need V3 over 2G. Over 2 times 32.2 feet per second squared. Okay, so this one becomes a little problematic because V3 is harder to get at, right? We don't have V3. It wasn't given. V2 was given. So let's go ahead and get V3. And the way we're going to do this is we're going to do continuity. So this was kind of the easy way to do continuity, but there's another way, which is in equals out plus accumulation. So in this case, what I have coming in is Q1. So I'm going to do rho Q1 coming in equals out, which is going to be rho Q2 plus rho Q3. Okay, that's what's flowing out. Okay, we note that the rows are all the same, so those are going to cancel. So Q1 is V1A1 equals Q2 V2A2 plus V3A3. Okay, so V1A1, well, actually, they gave us Q, didn't they? They gave us Q1, so we don't need to do all that. So let's just make this 4CFS. Okay, V2A2. Well, V2 is 40. Oh, that needs to be an equal sign, doesn't it? Sorry, there's a child screaming at my dog downstairs. I don't know if you can hear that. Okay, equals. Come on, punk. Equals. Okay, 40.74 feet per second times the area, which is pi times 3 inches squared. So 3 inches is 1/4 of a foot squared over 4. Okay, plus V3 times area 3. Area 3 is 1/3 of a foot because it's 4 inches. So pi times 1/3 foot squared over 4. Okay, we could solve this equation, and what we're going to end up with is that V3 equals 22.92 feet per second. Feet per second. Okay, or FPS. Okay, so we're going to take that, we're going to put it over here, 22.92 feet per second. Okay, back into our Bernoulli equation, and we'll solve that, and P3 comes to 2779.2. That's pounds per square foot gauge. And we'll go with P3 equals 19.3 PSI gauge. Okay, either one of these is acceptable. I usually prefer to work in pounds per square foot. Okay. All right, so that's it. Hopefully these did not hurt your brain too much. Obviously, this one's very difficult. This one's a little bit easier, and we're gonna build on this. So make sure you work on these problems. They're gonna get harder and harder. Well, sorry, the Bernoulli problem is not gonna get harder, but what's gonna happen is we're gonna replace Bernoulli with energy equation, which is very similar, but we're gonna take into account friction. So make sure you understand Bernoulli. And what's gonna happen is in like a week or two, Bernoulli will all of a sudden just kind of slide into place in your mind. It's gonna be a little bit complicated at first. So again, take care of yourselves, take care of each other, and we'll be back. So have a good day, all right, or night, or morning, or wherever this video finds you. Good night and goodbye.